Section 3, Objectives. Describe a conjugate acid, a conjugate base, and an amphoteric compound, and explain the process of neutralization. Bronsted-Lowry acids or reactions involve conjugate acid-base pairs. The Bronsted-Lowry definition of acids and bases provide the basis for studying proton transfer reactions, which we're going to be studying in this section. Now, just to remind ourselves that a Bronsted-Lowry acid was a proton donor. We had that in the last section. A Bronsted-Lowry acid is a proton donor. A Bronsted-Lowry base is a proton acceptor. A Bronsted-Lowry base is a proton acceptor. Now, suppose that a Bronsted-Lowry acid gives up a proton. The remaining ion or molecule, after it gave away its proton, what's left can, which is now part of the products, could reaccept a proton and act as a base. So whatever was formed could act as a base and reform the acid. Now, such a base is known as a conjugate base. Now, conjugate, it just means it's kind of connected with it. It has parts that are similar to it, like the tenses of a verb are all have to do with the same thing. The species that remains after a Bronsted-Lowry acid has given up a proton is called the conjugate base of that acid. So here's an example that we can use. Here we have hydrogen fluoride reacting with water, and after the hydrogen fluoride gave up its proton, all that's left is the fluoride ion that we see right after the double arrows. The proton was accepted by water, and water with this extra proton becomes the hydronium ion that we see on the product side way at the end. So hydrogen fluoride was an acid, or hydrofluoric acid since it's in water, gives up a proton, and in the process of giving up a proton, what is left is a conjugate base. So that fluoride that you see right after the double arrow is a conjugate base. Now in this reaction, water is acting like a base because it's accepting a proton. So it's a Bronsted-Lowry base, and it's going to accept the proton, and by accepting it, it's going to end up forming a hydronium ion, and that is an acid because it's forming something that actually has a proton that could be donated. So the hydronium ion is the conjugate acid of water. Water's the base, and the hydronium ion in this situation is an acid, the conjugate acid of water. The species that is formed when a Bronsted-Lowry base gains a proton is the conjugate acid of that base. So water was the base, we said. It gained a proton from the hydrofluoric acid molecule and forms the hydronium ion that we see way over on the right. So water is acting like a base, and it forms a conjugate acid. So in general, Bronsted-Lowry acid-base reactions are in equilibrium systems, meaning that both the forward and the reverse reactions occur. And they involve two acid-base pairs known as conjugate acid-base pairs. So if we look at our example that we've been had here, hydrogen fluoride was an acid, and it formed a conjugate base, which is base 1 on the right. So the acid 1, goes with base 1. Hydrogen or hydrofluoric acid is the acid, its base, its conjugate base is the fluoride ion. Water is a base, and it forms a conjugate acid. By gaining a proton, it's going to be H3O plus the hydronium ion. So notice that the base and the acid both have 2's after it because they belong together. So those subscripts that you have right there help us to know what are the pairs. So acid 1 goes with base 1, base 2 goes with acid 2. So HF and the fluoride ion go together, and water and H3O plus go together. So in every conjugate acid-base pair, you'll notice that the acid always has one more proton than its conjugate base. So on the left we have hydrogen fluoride. It has one more proton than its base, F, negative. And H3O plus and acid has one more proton than water does. Now in this chart right here, we're looking at these pairs of conjugate acids and conjugate bases. On the left column we have the acids, and if you'll notice that the names of all of those down to nitric acid have little asterisks after it, and if you look down at the bottom you notice those are all called strong acids. So the strongest acids on the left side are at the top. The weakest acids are at the bottom. Then on the right we have the bases. And now they're not, remember this is not Arrhenius's definition of a base that has an OH. Is the Bronsted-Lowry definition of a base. Now, let's take sulfuric acid, which is I think the fifth one down, is a strong acid, H2SO4, and if it gives up a proton, it will form its conjugate base. And notice just on the same row to the right you have HSO4, hydrogen sulfate ion, and that's the conjugate base of the acid, sulfuric acid. And then hydronium, if you go down about 3 or 4 more, you have hydronium ion, has a proton to donate, and when it donates, so it's acting like an acid, when it donates that, what will be left will be just water, and it is its conjugate base. And so the pattern is that on the left side, the strongest acids are at the top and the weakest acids are at the bottom. And on the right side, the weakest bases are at the top and the strongest bases are at the bottom. The extent of a reaction between a Bronsted-Lowry acid and base depends on the relative strength of the acids and bases that are involved. So we know hydrochloric acid from the previous chart is a strong acid, and it gives up a proton readily. That's why we call it strong. It readily ionizes. And therefore the ion that's produced after it gives up its proton or its hydrogen ion has little tendency to attract and retain that proton. Otherwise it wouldn't have left in the first place. So consequently, that chloride ion is an extremely weak base. It's the conjugate base, but it's a weak base. So we have a stronger acid, HCl, giving up its proton and forming a weaker base, chloride negative, over on the right. And then we have water, which is accepting that proton. It readily accepts that proton, which is a base, and it will form its acid, its conjugate acid, which is H3O plus. So what are some conclusions that we can draw so far? The stronger an acid is, the weaker its conjugate base, and the stronger a base is, the weaker its conjugate acid. So if we start out with something on the left column toward the top, its conjugate base on the right column will be at the weak end of its chart column, and a strong base on the right, which will be down towards the or closer to the bottom, will form a weaker conjugate acid, which will be lower on the acid side, toward the bottom of the acid side. So let's take a very strong acid. This is perchloric acid, one of those that we've used as our strong acid example. Has a proton to donate, and it will, when it donates its proton to water, which is acting as a base, what will be left after perchloric acid gives up its hydrogen or its proton is going to be way over on the right, the ClO4 negative, the perchlorate ion. The water, which which accepts that proton, is functioning as a base, and what will be formed after having accepted that proton is a hydronium ion, H3O+. So we have a strong acid producing a weaker base on the right side, and then we have a water acting like a strong base, and it's producing a weaker acid. So there's a strong attraction between the water and that hydrogen ion. It doesn't want to give it up readily, so that's what makes it a weaker acid. Let's look at one of our weak acid examples that we've had from early in the chapter. This CH3COOH is acetic acid. The H on the end is the one that actually it's capable of donating. And this is acetic acid, and so it's going to donate that hydrogen ion to the water, which is functioning as a base. The acetic acid at the very beginning is going to be acting like an acid, but we know it's a weak acid. And what's left over after it gave away its hydrogen ion or its proton is the structure that's way over on the right, the CH3COO negative. That's the acetate ion, C2H3O2 ion, and that is a stronger base because it will accept a proton.